Well, thanks very much for that, Arnie. We could take a short break, but I think perhaps we'll have a few questions, then maybe take a break, and then we can have a general discussion while people are wandering off and getting cups of coffee or whatever. How about that? So, any questions? Any questions? Any burning questions anyway on any of that at the moment? Viv.
Just like with that model, how do electrons get subjected to the special relativity corrections as they move?
Well, they're intrinsic to the algebra. So the special relativity corrections have to come in terms of the vector. Well, the vector part of it is the vector potential. The bivector part is the fields. The scalar part is invariant scalar part is the pivot and the Quedge-Hog. And the spin part is the trivector potential part of the thing, which is the thing which Arnie's mostly been talking about. And of course, you can't really talk about going into the trivector potential until you define what a trivector potential is. But the relativistic transformations of each of those is intrinsic to the algebra. So if you look in a different frame, so if you let a general Lorentz transformation loose on the whole thing, it will transform each of those according to their nature. So the vectors will transform as 4 vectors. The invariants will be invariant under a Lorentz transformation, rotation. And the fields will transform as fields and do transform as fields. So and this is the reason for really forcing absolute relativity on the whole thing. If you've got some object which is coherent in one frame, and this is also the problem we have with a wave function in normal quantum mechanics, it's always referred to, it looks like something like ae to the I kx minus omega t, but that x and t is the x and t in a particular frame. And in order to do the transformations, you have to work to transform more than one thing. In this case, provided you keep everything with its proper form, the relativistic transformation transforms each and every one of those properly relativistically straight away, ensuring the integrity of the whole thing and the fact that it's relativistically covariant in all frames. So that's the reason for doing, it's because you're keeping the relativistic part of the of each object with its own proper form, which each of those forms transforms properly relativistically according to its nature. So that's how it does it. That's how it does it in practice. If you take a wave function and hit it with a Lorentz transformation. So that's why. It's because it's an intrinsically relativistic algebra. This is true of the Dirac algebra as well, but it's not true of the complex algebra. Complex algebra doesn't transform properly relativistically under a Lorentz transformation. You need to work to do that properly.
Could I just make a quick comment here? Just that this whole business about relativistic corrections. In a sense, if you look at things even in a two-dimensional spacetime, you can see that relativity is actually, at least quantum mechanics, is a result of the special relativity. And in order to get regular and non-relativistic quantum mechanics, you have to decorrect from relativity. Because what's really happening is the whole idea of the phase of the wave function actually comes from relativistic time dilation. It's part of the Lorentz transformation itself. Absolutely. So we sort of the pedagogy around quantum mechanics is we all learn this stuff in the non-relativistic context first, and within theoretical physics, it seems to be everybody thinks of quantum mechanics as being a distinct thing that you can correct to be relativistically correct, but it exists by itself. But in actual fact, I think when you look at it a bit more closely, you find that it really is the Lorentz transformation that generates the quantum mechanics in the first place. So if you did live in a classical, a Newtonian world, quantum mechanics would disappear as well. So the fact that John and Arnie don't have to fuss too much about the relativistic corrections because they start out sort of in the right place.
Thanks very much for that, Garnet. Yes, that's absolutely correct. And the thing is that you might think that you could do that in any other kind of context, but I think where a mistake is often made is in switching something to a specific frame and then seeing that problems arise and then assigning those problems to the difference between relativity and quantum mechanics. And there's been an entire field developed on this, which I think is mistaken from its outset in the fact that it has messed up the underlying mathematics by introducing a mathematics which is non-relativistic in a place where it should have been kept relativistic. But the problem doesn't come from the physics, it comes from the maths.
Yeah.
I don't think Viv will argue with you on that.
No.
I always look at Einstein's field equations and you shake your head and say, how can people just miss the maths that he got right? How can they miss it so badly? Physical explanations to maths, and then I use what maths required to show the magnitude of the physical effect. Anyway, that will always be a difference between us, John. And well, maybe it won't always, but
I don't think there is a difference between us here, Viv. I mean, I've developed this math to try and describe the reality I see, but the reality I see is always more important than the mathematics I try and use to describe it. In fact, the struggle that we're having here, Arnie and I are having here with the spin stuff. Remember, nobody's looked at this, been able to look into spin in this kind of detailed way before, because we haven't had the trivector potential stuff to play with before and have a look at how this might happen at a detailed level. And a lot of the results that Arnie's talking about, you've got a couple of sets of spaces here. You've got an odd set of spaces and an even set of spaces. And the two sets are not entirely distinct from one another because they are coupled by a set of linear equations, by differential equations where one of them is essentially a differential of, well, the odd space is a differential of the even space and vice versa. So it means that you have to be really quite careful and to not double count, because if you're looking in spin space and looking in magnetic field space, electric field and magnetic field space are even spaces, whereas spin space and vector potential, flow space are odd spaces. So you have to be a little bit careful in that if you're looking at what's happening in the spin space, it's actually, and what's happening in the electric field space, eventually they have to agree because one is a derivative literally of the other. So, and the other thing is that one is looking at different kinds of energies. When you're looking at positronium, you're looking at an energy which is comparable to the energy of a hydrogen atom, to the sort of 13.6 electron volts, a factor of 2 in there, that's all. And in size, they're comparable sizes, much, much bigger sizes than the electron positron themselves. They're about 10 to the minus 13 meters. Atoms and positronium are about 10 to the minus 10 meters. They're also much slower. So the frequency and the energy scales at positronium scales are quite different to those at elementary particle scales. So you do have to be a little bit careful, and we're just beginning to explore the physics of spin interactions, of spin inclusion and spin exclusion interactions in this. However, if you go to something, remember I'm an experimental scientist first and foremost as well, not a mathematician or a theoretical physicist. And if you go to experiment, then you know that very peculiar things are happening with the Pauli exclusion principle. It's not really it's taken as being a principle only because there's not been a mechanism up till now to understand what it is, but it's really a very strong force. And you see that in experiment. If you look at things like the zero gradient synchrotron stuff, which was done many decades ago, even at Argonne National Laboratory, and work flowing on from that with polarized proton scattering, you see huge anomalies in that, which have not been explained to present. This is the spin puzzle for the proton that was a big discussion in the end of the 70s, beginning of the 80s, and still not been resolved. And things like the EMC effect as well, which I was also involved with the EMC. I worked in that collaboration. These are big mysteries in science in terms of the way these things actually work, and it's that we're trying to get to grips with at the moment, to see what spin does at the detailed level in terms of bosons and fermions, the creation of bosons in spin inclusion, the repulsion of fermions in the Pauli exclusion principle. So it's that kind of thing that we're trying to look at really for the first time. And I don't think we'll get it right at first. I think this is a very, very good attempt right at the moment to think about how these things might fit together, but they really should be subject to experiment and subject to thought and see if we can find out what's really going on. We know some of the broad brush things, the fact that exclusion happens and that inclusion happens in terms of such things as superconductivity and Bose-Einstein condensation and so forth. But these are quite, when we're talking about that kind of inclusion, we're talking about the low energy end of things, not the high energy end of things where you hit things together, where the length scales for the electric field interaction are very, very short, and because it's inverse square, they dominate. So in high energy scattering, it's of electrons on electrons, it's charge scattering that's important. Protons less so, because one can resolve 10 to the minus 15 meters, which is the size of a nucleon, and then you can get inside the spin puzzle. And it's those sorts of things that need to be dealt with next. Yep, Lyndon.
Deep in marking A-level international papers, and one of them there is the photoelectric effect. I'm just thinking, you've got the electron inside on the surface of the metal, that thing. Photon comes in, releases it, and it says the same electron out. What happened to that other photon? They're saying that the electron absorbs a photon.
Well, yeah, the hydrogen atom system absorbs the photon. So it's the atomic system that absorbs the photon. So we're talking about, in the case of hydrogen, 30.6 electron volt photon will come in and will eject that electron from an isolated hydrogen atom. So it's not the electron that absorbs the photon. It's the electroproton that is the hydrogen atom, or is the multi-electro, multi-proto, multi-neutron object, which is the molecule or the atom that's doing the emission. So there, what's happened is the photon has given, it's a boson, has given up all of its energy to the atom, or to the atomic system, to the system, to eject the electron from that bound state system. These photons are much lower energy than electron internal photons.
Okay.
Yeah.
One more.
Yeah, certainly, go.
Okay. With spin superposition, where it states that the electrons have both spins at once, but you don't know what it is until you measure it. I read somewhere that that's actually been proven. So how does that fit in when you're saying that they have a separate structure for spin up and spin down?
I think, are you talking about the fact that if you measure the spin of an isolated electron, you can either get spin up or spin down depending on how you measure it?
That's what I'm saying. It's just
yes.
spin.
I think the reason is that what you're doing is you've got a system which is following a quantum bicycle motion. It's tumbling all over the place. Now it has an intrinsic spin of the photon, which is going either leftwards or rightwards inside the photon. That's either spin up or spin down for that thing. But then if you try to do a measurement of that with an external thing, with an external polarizer, where you're fitting the polarizer anywhere in 3D space, then what you're going to do is you're taking something which is rotating extremely quickly and tumbling over itself, and you're sticking like a pole through a bicycle wheel. You're sticking a particular direction, and you're going to measure the spin about that particular direction. Now, what you're going to get is you're either going to get so that spin will unravel and will wrap around that direction, and it will either wrap around leftwards or rightwards, depending on where you are with respect to that photon, with probabilities that are intermediate. So it's like trying to catch a spinning tiger by the tail. It's spinning around in some direction. You put your hand in and try and grab it. You don't know whether you're going to be spun leftwards or spun rightwards by that grab, but you're going to get one or the other, and all of the spin will condense onto that direction, because you have this tumbling, twisting, turning motion, and you're trying to grab onto that. So you have all possible probabilities. So it's simply a probability distribution as to whether you get spin leftwards or spin rightwards, depending on whether you come in from one direction or you come in from another direction. That will switch all the probabilities for that. So that's where it comes from. It's not because it's not a particular spin direction, that it's not going round and round like a solid object, but it's something which is internal to the object, which is then twisting and turning and tumbling. It depends on which axis you grab it as to what you're going to measure.
Well, the question is, Arnie has stated that there are the two states of spin on electrons are due to a physical difference. That's what I understood him stating. And all I'm saying is that in the spin superposition experiments, that I have read that it has, but I don't have the reference, has been verified that they found out the electron has both states of spin at the same time, but you only know which one it is when you measure it. And that's, as you know, my model, that's just the other side of the page image, whereas the difference between a positron and an electron is one is a mirror image of the other.
I think the difference is that imagine you have a set of helium atoms which have dielectron included pairs where you have one spin up and one spin down. You have spin 0, so then they're in the singlet state, and start and have a look at that. It's true that you don't know which photon's carrying spin up and which one's carrying spin down. So which electron is carrying spin up and which one's carrying spin down. And in that case, if you try and measure the spin of one of those things to be spin up or spin down, it'll be 50-50 spin up or spin down, whichever direction you try and measure it in. So and that will be saying that both electrons are carrying both spin up and spin down. Yes. But in fact, you know, one of them's carrying spin up, the other one's carrying spin down. So, but you're measuring that with respect to something.
Okay, I'll leave it for somebody else to ask a question.
Well, also the other question that I have back for you, Viv, then what would be preventing the electrons from repelling away from each other? What's keeping them together if they have like charges? How do they bond?
So you're saying what keeps electrons together? Why do they pair? Is that the question?
Right.
Yeah, okay. Well, you've got to bear in mind that when something is rotating, you've got an electron at basically rest. You've got its whole mass moving at the speed of light at a radius of what, 130 femtometers or something. That's one all hell of a gyroscope. Now, you all know mechanically, you get a very powerful gyroscope and just try to move it like this, you can't. But as soon as you put two gyroscopes, one touching the other, you can do what you like with both of them because they can transfer angular momentum. And I'm saying that the reason that they pair is because, well, there are photons everywhere in space, and their charge is the emission and absorption of photons. They're continually emitting and absorbing photons. The photons have a spin of h bar. If they've got a pair, if you get a pair of them together, they can quite easily just exchange angular momentum and quite happily go doing what they want. If you've got a single electron, it's not going to change direction very easily.
Yeah, but that's the case here as well. You always have the inner orbital of any atom has a spin 0 state. It's a dielectron boson. You've got something which is spin 0. So you have a matched pair of spins and an overall spin of an overall angular momentum of 0 for those things. So it's not that you have a couple of random direction things which are touching. They are counter-aligned in the space in which they in the spin space, in whatever space they're spinning in. More questions.
What's the diameter of your electron then?
Sorry, Viv?
Or radius of your electron?
The radius of the electron is about 10 to the minus 13 meters, 2 point something 10 to the minus 13 meters for an isolated electron. In an atom, it's 10 to the minus 10 meters. In solid state, it's quite large. I mean, it's semiconductor, it's about 40 nanometers. In superconductor, it can be very large indeed. So it's a very variable. It depends also when you're asking for the radius of the electron. It depends if you're asking for a radius in terms of normal space, and you try and measure that radius, then that radius is immeasurably small. It's a point-like interaction that you have with electrons on other electrons. So it's not a fixed quantity. It's not something that you can stick a gauge on and measure, because you don't have any. The only thing you can do is bang other electrons against it. So if you scatter electrons on electrons, then you see something which is 10 to the minus 18 meters in terms of the effective, in terms of the point-like interaction between two electrons. This isn't to say the two electrons are 10 to the minus 18 meters, because they can't be, because electrostatically that would be too much energy. But what it's saying is that the interaction has to be spherically symmetric and concentrated at its center. So that's what point-like means. It doesn't mean that the thing is that small. So the question is, or turning the question back, is what kind of experiment are you talking about to measure the size of an electron?
Well, I know. I mean, basically, the low energy and this de Broglie wavelength is quite long, many nanometers. As the energy goes up, well, you know, the work I've done, John, as the energy goes up, the diameter of the electron, and indeed of all particles, diminishes according to the special relativity correction, starting out at whatever it is, about 1.39 times 10 to the minus 13 meters at rest. And you apply your 1 minus b squared over c squared correction to that. When you get to many GeV, 10 to the minus 17. When you get to many TeV, it's 10 to the minus 18. That's just the relativistic correction.
It is exactly that. What you're doing is and in my original model, what you're doing there is you're looking at something which is really a photon going around and around in circles. And as you look at that relativistically, then you only see the stuff coming towards you because it's light speed going around the whole loop, and that shrinks exactly relativistically. So it shows exactly that behavior. So you and I agree completely about that it's just the relativistic corrections that are making the thing smaller. And coming from the de Broglie wavelength as well, because it's just a couple of terms that you have in the relativistic expansion of those, which is how de Broglie got to it in the first place, how got to his relation lambda is h over p in the first place. As Garnet was just pointing out, it's purely relativistic, the de Broglie size of the electron. So I've carried out experiments where I've looked at the size of electrons in the solid state in gallium arsenide heterostructure devices. And I published a paper back in 1990, an experimental paper looking at the size of electrons there, and they're 40 nanometers in size. So in terms of, yeah.
So do you think of that as a characteristic of the electron or of space-time?
Neither. It's a characteristic of the environment in which the electron finds itself. It's a characteristic of the crystal or of the atom. So what you're measuring, you're no longer measuring something which is an electron, you're measuring an electroproton in the hydrogen atom. You're not measuring an electron in the solid state, you're measuring a collective excitation of the solid state in which the electron is embedded in a matrix of positive ions at a much, much lower energy scale. So that energy scale is commensurate with its de Broglie wavelength inside the system, and it's measurably so. Its charge is distributed like that. So it's not a little point charge.
Well, yes. I mean, I guess that's what I'm getting at. But so can you throw away all the rest of the interaction, and then ask the same question? What about the behavior of the electron? Do you actually think of it as space-time, or do you think of it as, well, its name, it's electron. This is what electron.
I think that I hear what you're getting at, and I think it's a huge mystery, and it's a beautiful, beautiful thing. But I think that what the electron is it is a topology. It's a topology. It has a form, and that form gives you the charge, which you can calculate. And what you've done by putting the poor electron into a system like the solid state is you've created a system which is no longer an electron. It's now a multi-electron, multi-atomic core system, which still maintains the topology of the original electron. But the whole thing is relaxed. The poor electron was having to maintain itself when it was isolated against the whole rest of the universe. Now it's sharing that, a lot of that interaction that it has with stuff which is local, which is part of the crystal, which is resonant and harmonic. And the thing sinks into that, like sinking into a lovely downy bed, and it spreads out. It spreads out and becomes something which is a collective excitation, which is far, far lower energy than the electron originally was. Something like that must be happening.
Yeah, no, I agree entirely. But then again, take away all the interactions, take away that comfortable bed, because you then have to ask, well, okay, if none of that stuff is around, what the heck is the electron? And is it actually instructions from space-time, or is it something different?
Now you're asking, or I'm going to answer a completely different question. I think that half of the electron isn't in the electron at all. I think it's in its interactions. So I think that for an isolated electron, that what you're doing is you're interacting with the rest of the universe in the way that Feynman and Wheeler were talking about, and in the way that Carver-Mead talks about as well, in terms of a transactional interaction. And that means that half of the time, I mean, the thing is throwing bits of itself out across the universe and getting other bits coming in, and half of it at any one time is in transit in terms of that interaction. And if you calculate, we did a calculation, Martin and myself, where we imagined that the electron was like a perfect conducting sphere, so that it was shielding the inside of the electron. And then we imagined the electron interaction with the rest of the universe, and looked at interactions with particles, looked at the probability of those interactions in quantum electrodynamics, and then integrated overall existing 10 to the 80 or so existing particles. Then you get a force for that multiple exchange, which is roughly a Newton, which is about what you need to make the thing go round and round, which is pretty much exactly what you need to make the thing go round and round in circles a radius of 10 to the minus 13 meters. So the electron is, if you isolate it and stick it out in space somewhere, it's interacting with everything in the whole universe all of the time. It's not limited. It's only limited. So every successive shell interacts just as strongly with that poor isolated electron as every other one.
John, I think what it could be summed up by that when you're talking about the dimensions of the electron, you have three factors to take into account. One, the de Broglie wavelength, two, the diameter you're talking about, and the third one is the environment in which it's in, because depending on the environment, it can occupy quite a large space.
Yeah.
I think that's right, but I think they're related. I think the environment is affecting the effective. When you're talking about the size of an electron, it's kind of a non-question, because it's not. What we're talking about is we're talking about its interactions, because it's only by its interactions that we can know it.
Yes.
So what we have to do is we have to say, what is the interaction that we're having with this object, and how is it interacting with my measuring device? And it's that you're measuring. It's not the actual properties of a little hard ball sitting there with a charge in space that doesn't have any origin, except for the fact that you granted it a quantized charge of 1.
Also seems to imply that the electron will be a different size in electric field space than it will be in magnetic field space versus spin space, because the interactions have a different strength and a different distance that they're operating at.
That's right. But remember that the only space in which you can put your ruler is in inverse space. Because if you're measuring something with a ruler, what you're doing when you take a ruler is you're saying, here's a ruler. So if I want to measure how tall I am, what I do is I divide my height into a series of ruler heights. So I'm doing a division of me by the ruler to get my size. I'm looking at how this thing relates to me by doing a division, but we can expand that to doing a differential, to saying so what's the rate of change that this thing invokes on me? You're looking at rulers and clocks in terms of measuring something. So when you measure something, what you're doing is you're splitting it up by saying, what is that relative to me? And that's a differential, that's a division that you're doing. So and that differential is the interaction. So the thing is, we don't live in the world of objects, we live in the world of interactions. And so,
okay. I guess so. So what I was trying to poke at really was the fact that basically all of this stuff is actually inherent in the Lorentz transformation. And
yes,
yeah,
that's
absolutely.
And
basically the signature of space-time is what gives you all of these funny effects.
Yes, that's right. It's the signature of division. It's the basic process we're using to understand all of this.
That's right, and it comes out, I think, with that very old mathematical problem that you have, in a sense, points and lines, and you can't construct lines from points. You need the object.
Absolutely. Yeah.
Differential. This thing.
Absolutely.
And just one other last comment is that one of the things that is confusing about constructing all this stuff is we think in terms of points and lines in terms of world lines. Okay, we think of it seems automatic that we can think, oh well, just take the center of mass and follow that, and that will give us a world line. That's not what happens in Minkowski space, right? It is actually, in a sense, areas as opposed to lengths, and it's because it's all about areas in space-time that you do get these funny stuff.
That's right. Everything's a division. It's not just an area. It's kind of like, it's not A times B, it's A divided by B.
Well, yes.
Or a little bit A divided by a little bit of B.
But in a sense, the dimension is wrong, right? The dimension of thinking of the world line as being a line. Yeah. I mean, it's corrected clumsily and non-relativistic by saying, okay, well, okay, instead of real numbers, we'll go to complex numbers.
Yeah.
And
it's too simple.
But that in the end isn't good enough. The reason it isn't good enough is because when you go back to Minkowski space and you say, okay, let's put points on a world line, you just look at what happens between the points on the world line. You have the causal area, and that's the thing that you have to approximate by the differential.
Absolutely right. Absolutely right.
You know, what gives you all this stuff. So.
It does, and as soon as you start doing differentials, you're also doing very nasty things to your measurement stuff, because as soon as you do a velocity, a light speed velocity, then everything, all distances go to nothing. So then what's your distance? It can be anything. So if you do it properly relativistic, well, the only way to do it is properly relativistically, and then it has some sense to talk about these things. But we're talking about length scales that are defined by an energy scale, E is h, well, defined by a frequency scale, in fact, by an E is h nu scale. And that's your clock. And you've got to look at what the clock is telling you, is how that's dividing time up. And that is not as simple a process as most people think it is. I mean, I know I've learned a lot from you on this one, Garnet, and I'm completely with you on this, but that's exactly where the problem lies. It lies in that we're really looking at areas, or more properly, inverse it, well, areas with an inversion.
Right, so it's just what you can't do with a dimension down, right? That's
right.
It's lovely stuff. So
it's complex, but it's beautiful. I must say that I'm quite okay thinking in sort of vector space and thinking in bivector space now. I've kind of got some facility with that. But I have to admit that when it gets to trivector space and the stuff that Arnie and I are trying to do now, that my imagination begins to go a little bit, oh my God, what is this stuff? And I think Arnie's done beautifully in sort of thinking about the thing being a twist and being a compression, and then that having a time differential and having some motion associated with it, begin to get some little bit of a claw at the fingertips into what that space looks like in terms of that space and how it can interact. I don't think we've got everything. I don't think by any means, Arnie and I have got everything right in terms of the spin interactions yet, but it's a wonderful new playground to get into, and a wonderful new dimension to get into, to try and think about it.
Absolutely.
Okay, so let me make one remark regarding the size of electrons. So there is a direct way to measure it by scattering. The size of particles you can measure by scattering, and the cross section it can be imagined as a surface. So there are these kinds of experiments, electron positron experiments. So the problem is that there is huge energy in gaps usually. But if you interpolate it to the mass of resting electron positron, then you get a few femtometer size of the electron. I can show you. I have the slide.
Yeah, no, I know the experiment, Jarek, and yes, but you have a problem in that the cross section, of course, is very, very large if you have an inverse square force. But what the experiments show is, you're right, you get down to about, well, it depends. If you do electron scatter 10 to the minus 15 meters, I would have thought 10 to the minus 18 meters was more what you got down to in terms of these things. But I'm prepared to look at experiments to say that's bigger.
So yeah. So there are 10 to minus 15 meters. They are usually based on the G factor. So there is a problem with the G factor argument. So that they come to this Delmes article, which they had this extrapolation from 2 points, draw a parabola, and got that.
I've seen that. I'm not happy with that.
Nonsense. But people using this 10 to minus 8 meters usually have to use this G factor argument, which is complete nonsense. From the other side, there is this scattering. Scattering suggests if you do the extrapolation to mass of resting energy to resting electron plus positron, to remove the Lorentz contraction.
Yeah.
Because you have many gaps, so you are the size of a resting electron. If you do the extrapolation to resting, then you get size in 1-2 femtometers, something like that. Another argument for finite size of electron, so that it is not a perfect point charge, is then running coupling. So for perfect point charge, there would be no running coupling. Running coupling is the formation of alpha. That it becomes a bit larger for very high energies. That means very, very low distances. So for perfect points, you have no running coupling.
Yeah.
So running coupling is a very, very, very good, very, very important factor to understand the size of electron. It's the formation of Coulomb interaction for very small distances. And it can be done for these Photon models. Faber has nice paper showing that he gets the proper running coupling.
I think the numbers that come out there for the running coupling constant are a bit smaller than 10 to the minus 13 meters, aren't they? So
yes, I think so. Yeah.
You start to, and I think that the reason that what you're doing is if you're getting down to that size scale, you're getting down to, well, the Compton wavelength. It's of the order of the Compton wavelength of the electron that these things begin to matter. And I think that what's happening there is you're beginning to get an overlap. You're beginning to get the electron field distributions, the inside field distributions of the electrons, this double looping thing, are beginning to overlap with one another. Once they begin to overlap with one another, you get an interference, and that interference is going to increase the energy and increase the coupling. So I think that's what's happening.
I put on chat the paper which for topological defects finds this. So we need Coulomb interaction with the defect with very small deformation in very small distances. And in this article he gets Coulomb interaction, and for very short distances you get this deformation like running coupling.
Another argument for the size of the electron is the anomalous G factor of the electron, and
yes.
and you know, about 1,000. It's about for those of you who don't know, this is a ratio between the it's called the gyromagnetic ratio. So it's a ratio between the spin of the electron as measured, the Dirac spin of the electron, which is exactly 2, and that which is measured, which is a fraction different to that. The fraction's roughly alpha over 2 pi. Well, the first order correction is alpha over 2 pi down, a factor of about 1,000. So alpha is about 1 over 137. 2 pi gives an extra factor of 12. So you end up with a factor of about 1,000th of the mass of the electron. Now, that's a factor which you can calculate in quantum electrodynamics to n decimal places. But I think the physical, but if we're talking about the size of the electron, what we're talking about is we're talking about something which is really spinning. So it's going around and around in circles. Now, if you have a look at an object which is spinning at the speed of light, you know its frequency because you know its energy, 511 electron volts. So you can work out how fast it's spinning. So if you look at how fast it's spinning and then have a look at the electric field out, so you end up with a radius which is lambda c over 2 pi, lambda c over 2. So if you take the radius of the electron, which is the fastest it could possibly be going round and round, is it could be oscillating backwards and forwards by a wavelength, and that's the fastest it could get from one side of the electron to the other.
Yes, so the frequency you are talking about is this 10 to 21st hertz.
That's right, that's a 10 to 21 hertz. So if you take 10 to 21 and then transform that to a radius through the speed of
Compton wavelength. Yes.
Exactly, so it's a Compton wavelength diameter, half a Compton wavelength radius. Then integrate the electric field energy outside of that, you'll find that it gives you the first order correction to G-2. So it's quite a simple integral. It's a very nice sum. It's a very nice integral to do. But that means that what it's saying is that a part of the electron is not rotating, and the reason it's not rotating is it can't go around faster than the speed of light. So anything outside that's outside a rotation horizon. So one has to discount that, and that's the factor of alpha over 2 pi.
So personally, I don't think about it. There is something rotating around, but later that.
No, I know it's not usual. What do you think?
The field itself, it's rotating.
Yes, I agree. It's not a little point going round and round. It's the field which is switching, and it can't switch faster than that. That's right. Yes.
Well, the thing that fascinated me, John, after your talk a few weeks ago was when you mentioned your calculation of the charge of the electron, and that when the two rings of the torus were superimposed, essentially you're going on the same path that was 0.91 e, and then as you opened up the loop, the charge got up to like 10 e or something. So that implied the question to me, well, what's the thickness of the torus when it's exactly 1 e? And your answer was lambda c over 4 pi, I think, if I'm not mistaken.
Yeah, but that wasn't my answer. That's Jarek who first came up with that number. And if you've got the third edition of his textbook, you'll find there's a chapter on that. And he was trying to develop a quantum electrodynamics. And he from that was saying that one needed to put a cut. There are divergences that you get, infrared and ultraviolet divergences, when you have a point electron as opposed to point-like electron. And in order to get the numbers to match, he needed to put a cutoff of lambda c over 4 pi. So he was the first one to come up with that number, as far as I know. There may have been people before that, but he used that thing as a cutoff and got some sort of electrodynamics from that. But Dirac was never happy with quantum electrodynamics. Well, neither was Feynman. I think you need to be careful, though. Remember, these are all just models of what's happening from a particular point of view. If you look at the thing from the electric field point of view or from the size point of view, you're really looking at different things, and they're related to one another. So so it isn't that it is one thing. It's not. It is what it is, and we have to try and suss it out in terms of something that's really a very complex object. So, but I think the rotation horizon thing in terms of G-2 is a very strong argument for the proper origin of the gyromagnetic ratio. And I think that, but I think the charge thing, you see, the 0.91 charge that we calculate is very model dependent, and it's from an old model of Martin and mine, where we had all of the energy being a localized photon of the thing. There'd been nothing else. So that was a conjecture, really, that, well, it's not physical because something's got to be holding the electron together. Now, we're a long way forward from that at the moment. And I think if I calculated the charge of the electron now, it wouldn't be 0.9 electrons. It would be about half the electron charge, because I'd put the other half into pivot and Quedge-Hogg. So then you need the thing to have some size in order to get the charge up to exactly the electron charge. But I think that whole question relies on a proper model of what the electron's actually doing in 3D, and that's going to be computer modeling before we can really answer that question. But I think the reason all charges are quantized is because they're all interacting with one another, and the strength of interaction for any, they just act as bookends for photons. And so the reason that stuff's quantized is because if you have a charge which can, if you have an interactor, it will expand or shrink so that it's interacting at the same rate as every other interactor. If it interacts more quickly, then it's emitting energy, and if it interacts more slowly, then it's absorbing energy. It's just changing size, so it is exactly a 1e charge every time. So I think whatever the charge is what the charge is. It's not. Okay, there's a relationship between Planck's constant and the charge, and that's an interesting thing. But that's what you're saying, is you're saying there's a relationship between energy, or if you like, mass and charge. And of course, that's an important thing. That's one constant less. H bar or E, choose which one you like. You can derive the other in terms of the other one. So so in that interaction picture. So again, it's a model. So you have to you have to do these things modulo the model. So so I don't think Martin and my model was the whole story back in 1997. So that's why I'm a bit reticent about trying to do a calculation which would give an exact number for the charge, but I don't think that means very much at the moment. I don't think we're far enough along with knowing what the wave functions are like for these things.
Charge appears mainly in Coulomb interaction. How do you get Coulomb interaction?
But you get the Coulomb. The way we got it originally was by taking that photon, which is twisting, taking the energy of the photon, putting it into a double loop, imagining, so we've now got the electric field of the photon, instead of rotating through 180 degrees, it spirals. We've now got it pointing outwards all the time. So it follows like, so when you do that projection onto ordinary space, what happens is the electric field vector follows like the seam of a tennis ball. If you've seen a tennis ball's kind of like two parts with a seam. It goes around like the seam of a tennis ball. It traces a path in three-dimensional space. What you then do is put a sphere around that and integrate. So you then integrate that field, and that gives you a charge at the radius where it becomes outward directed, which is the
Gauss law.
Yeah, just from Gauss's law. Now, you might think that depends on the size of the electron, but it doesn't. It turns out that if you do the integration, it doesn't matter how big it is. It only depends on the topology. So the thing is that if you put a smaller energy into the thing, that means a small electron, a 10 to the minus 13 electron, would have the same charge as a 10 to the minus 10 or 10 to the whatever size electron. They all have the same charge because the length scale cancels. It turns out when you do the integration, cancels identically. So the charge is not a function of the size; it's a function of the topology. So
yes, I agree that yeah. We need to make that the Gauss law counts topological charge, and we do it as this Faber-Hubbard article attached. So there is this problem that if you go down to the zero radius, then energy of electric field alone goes to infinity.
Exactly. So that's clearly something which you mustn't have. We have a length scale cutoff at lambda c over 4 pi, which is fine. It puts you well within the classical radius of the electron. Or well outside the classical radius of the electron, sorry, it's much bigger than the classical radius. So
I have a question. So what are your thoughts on other elementary particles like neutrinos or muons?
That's a lovely question. Yes, which there's a very, very long answer, Chantal, I'm afraid. Well, I think neutrinos, I've had different models of neutrinos over the years. So my current favorite one is what we have with a photon is we have something which is essentially one-dimensional. It's a rotation around a line. What we have with an electron is an electron is three-dimensional. It's 3 rotations. I think the neutrino has 2 rotations. I think it's a 2-dimensional object. And it's uncharged because it's then averaging over everything. But it does have some mass because it is following some path in space. My original model, this is predating Martin, this is back in 1979, did have a model for the neutrino, because what I was doing then is I was looking at the flow of electromagnetic energy around the surfaces of a cube. And it turns out that if you do that and you apply the kind of photon rules, but then offset them, so instead of electric giving magnetic here, you put the magnetic up half a wavelength, a quarter of a wavelength up on a cube, and then make it flow around the outside of a cube instead. There are two kinds of flows. One sort of flow goes around 5 sides of the cube, and I thought, oh, that's an electron. And the other one goes around 3 sides of the cube, like it's just on one side. And I thought, well, that's a neutrino. Now, these are just models, but I think the neutrino is a simpler kind of flow. It's not 3-dimensional, it's 2-dimensional. But I'm just making that up. That's just a conjecture, you know. I don't have any. Sorry, Viv. Did you have a?
So to understand neutrino, you need some mechanism, and the simplest mechanism is the beta decay of neutron. So you need neutron, and neutron should not be stable, and you should see that something what is released is the neutrino.
Yes.
What's your view on neutron and proton?
Well, I think we have to go to another part of Chantal's thing there, which is to talk about what I think hadrons are. Hadrons are much more massive than the electrons and protons and so forth. However, I also have this idea about what tauons and muons are as well, in that what they are is they're extra foldings of space, which I've described, I think, before. So what you have is the electron is something which goes around this double loop, but that double loop can then be looked at as just being a circulating thing. So if you can go fast enough that you can take that circulating thing and then force it into a double loop again, you then end up with something which comes, instead of going, if you go around a loop, you're going up one side and coming down the other side. So you have a flow up and a flow down, but you have that in 3 dimensions. For a 3-dimensional.
Promised to give me. Jarek had promised to give me a couple of hours in a few weeks to present all of that information, what a neutrino is, what a pion is, what a muon is, and so if you'd like to come and view that, I think that'll answer all your questions.
That would be great, yeah.
Yeah, I should say here that Viv and my models are a bit different when it comes to this. Viv's is more sophisticated than mine, so I think it's fair to say it's certainly more developed. But in my view, what's happening is that for the muon, what happens is instead of it doing this, it goes up, down, up, down. It has 4 flows in any one dimension, which is 4, but it's not 4 times 4 times 4. It's not a box of 4s, because the number of photon-like states are pairs. So if you have just going up and down, you have 1 pair, but if you have 4, you don't have 4, you have 6, because you have this and this, you have this and this, this and this. So you have these ones, you have these ones, and you have the 2 outer ones. So there are 6 combinations of 4 flows compared to 1 of 2 flows. So you should expect a particle with mass 6 times 6 times 6 the mass of the electron, which is very close to the mass of the muon. And then if you do the next thing, if you go to 6 flows, up, down, up, down, up, down, you then get 15 cubed, and that's very close to the mass of the tauon. Now, if you now look at hadrons, what I'm thinking is happening with hadrons is that with an electron, you go round and you come around a complete loop. So you do 720 degrees. What I think is happening with hadrons is you don't manage the full 720, that you miss a quarter turn. And what that means, it means the thing goes in, it does some looping, and then it comes out at right angles. Now, something like that is not a particle because it's unbound. But you can make it into a particle by taking 3 such objects or 2 such objects. So you can take 2 such, so you can have something that looks like this, that comes in, does some funny stuff and comes out at 90 degrees. And then you can do the reverse, goes round and comes back down again. So you can have something which is a left-handed loop and then a right-handed loop, and that would give you a continuous flow, left, right, left, right. Now, if you identify a left-handed loop with a quark and a right-handed with an anti-quark, then you would expect to see particles which are quark-anti-quark pairs, which you do, all the mesons. So I think that you can add meson Lego by doing that kind of thing, by saying that a meson doesn't exist unless it's a complete flow. And it has to be a complete flow, which is flow anti-flow or flow reverse flow in terms of the handedness of that flow within the loop. Then if you think about these things as being kind of Lego and you want to make Lego with just right-handed loops, then you can't do it with 2. Because you can put another right-handed loop in, but it still doesn't match. But you can go, so if you go X to Y, you can go Y to Z, but you don't get back to X, but you can do X to Y, Y to Z, Z to X, you can do 3 right-handed turns and get a complete loop. And that's what I think the proton and the neutron are.
So
But
we
I
have
think
two direction now. One is how to get nuclei, so to bind them against the Coulomb repulsion. The other direction there are thousands of baryons observed in.
Oh, you're right, there are. And I observed lots of them. I was at CERN for 7 years doing this kind of stuff. I saw loads of these things. They're all over the place. And yeah, no, the zoo of particles out there. So that's my model for what nucleons are. But then the reason, so what you have with the neutron is you have a neutron as a proto-electron. So you've got the 3 loops from the proton, but then you've also got an electron set of loops, which is another pair in each direction. So you've got something which now has far more loops, but a lot of these things cancel. Of course, you can share parts of this Lego when you start putting these things together, and you get a zoo of particles going up to about twice the proton mass when you do that. And you get one lightest particle, which is the neutron, but it's still heavier than the proton because it really contains an electron, and also the 2-dimensional part of the loop that switches one loop and changes its charge and gives you not the kind of charge that you get from the standard quark model, which is this 2/3, 2/3, 1/3. That's not the only possible model. You can also take you can also have a look at integer charge quarks and have a look at changing the charge from, so you can have 1 + 1 - 1 will also give you +1 for the proton. And that's an alternative model. And there was a measurement made to try and distinguish these two, to actually measure the charge on the struck quark from interactions with high energy muons. And well, that was me. That was my thesis. So I can tell you, we couldn't distinguish the charge on the struck quark. It looked smaller than either 1 or 2/3 or 1/3. So we couldn't distinguish that. And to date, I don't believe there's been any measurement made which has superseded the EMC measurement.
So the practical question here, what is the charge distribution of neutron? Usually I have seen that there is positive core and negative shell.
Well, I should say my favorite one for that is Viv's. So I like Viv's model more than I like my own model here, and I'd be very pleased to have him explain it to you as well.
My model is entirely in 3 space dimensions and time, uses only known physical constants and known physical properties, and we'll show what a quark, what are detected as what quarks are, that they are detected, same as muons. They're detected inside protons. I'll just go over all of that. And
yeah, I think we should pick up this discussion again after Viv's given his talk. Yeah. I think because I think he's got a lot to say about this, and it's very interesting stuff. Thanks very much indeed again, Arnie, for a very clear talk and taking things further in the spin direction here in terms of the theory. Well done. Good talk.
Thank you guys for joining us today.
Yes.
So it's just about the start of my day.
Yeah, it's time for you to have breakfast.
Okay, it's been nice meeting you.
Good to see all of you anyway. Look forward to seeing you at some conferences in the future. Take care, everyone.
Thanks.
Bye-bye.
Bye.